Hello and welcome to our Exoplanet mission debrief. Before we get started with our special guest, we're going to learn a little bit more about the extremely large telescope that is currently being built. In order for this telescope to see deep into space, it will rely on some really big mirrors to collect a lot of light. Let's check in with Remy at Safran to learn more about the ELT's mirrors.
The ELT is a telescope that will use 5 mirrors. As with the telescope, we want to see very far in the universe. The objects that we want to observe are very dark, so we need very large mirrors to be able to look at them. The primary mirror will be 39 meters in diameter. It cannot be made with only one optical piece, so 798 hexagonal segments will be manufactured and put all together to make this huge mirror. The secondary will be 4.2 meters in diameter. The M3 will be also 4.2 meters in diameter. The M4 will be very thin so that it is flexible. 6,000 actuators will be bonded on the rear surface so that the system can change the shape of the optical surface to make more accurate images. The astronomers want to study two major topics. The first one is the age of the universe. And the second one is the exoplanets. We have been able to detect them with the current instruments, but with the ELT, we will be able to look at them closer and to study them. ELT is a very complex system where many subsystems must work at the very same time. Safran is manufacturing the optics. There are two main activities in manufacturing this. The first one is to bound on the rear surface of the optics all the pads that will allow to interface the glass with the mechanical structure of the supporting frame. And this is done using metallic parts, metallic pads, and glue. And the second activity is to polish the optical surface so that the shape of this surface is exactly the same as the one that the customer has specified. It must be very accurate with no error, and we must measure and polish them down to less than 10 nanometers. To polish the surface, we need to measure them to know where are the defects. And then we have to polish the defects so that they disappear. And to polish them, we use a tool, and the tool will stay longer where the defect is higher, and it will stay less where the defect is smaller. In the end, we need to define the speed of the tool at any point of the optical surface. I'm Remy, and my company Safran Reosc polishes the mirrors for the extremely large telescope.
Today, our expert is Dr. Luc Sollitt, who is a senior research scientist at the Planetary Science Institute. Luc, thanks so much for joining us today.
Thanks for having me.
Luc and I are ready to take your questions, so put them in the comment section and we'll get to as many as we can. Luc, can you get things started by telling us a little bit how important the upcoming ELT will be and what sort of research you hope to get from it?
The Extremely Large Telescope program, there's going to be a few of them. The European ELT that you just heard about, plus potentially two American telescopes, one being built in South America right now, the Giant Magellan Telescope, and then another telescope planned for Hawaii, the 30-meter telescope. All of these telescopes have the capability to completely transform how we look at astronomy, because they are so much larger than the current generation of 8 to 10 meter telescopes. They have 10 times the light gathering power, which means they can look much further into the universe and at much dimmer objects. So we're going to be able to, for instance, exoplanets, we're going to be able to do a lot more with exoplanets than can currently be done. So that will be a fundamental change in astronomy.
We did get a couple of questions from Facebook earlier, so I thought I'd start with those. Teachers, if you're watching with your class of students, let us know who you are and where you are, and we'll give you a shout out. So, Luc, a lot of people want to know about Goldilocks zones, and what is it about those zones that make us think that there could be life on those planets?
Well, another way to look at a Goldilocks zone is it's also called a habitable zone. And what we think of as a habitable zone right now is a planet it's the area around a star where a planet like ours could exist. Specifically, what we mean by that is there could be liquid water on the surface. Because no matter what you're talking about for any sort of life, as far as we can tell, there's really only a couple things life needs. It needs organics, which are available, frankly, everywhere in the universe, including in large clouds of material way out in the middle of nowhere. It needs energy, free energy. Now, that can be anything. That can be sunlight, chemical energy, you name it. The other thing it needs, we think, is liquid water. That is certainly true of every life form we found here on Earth, and obviously that's our only data point. So what we think of as the habitable zone is, yes, water can be on the surface of a planet because it gets just enough heat from the star to be just that temperature. If it's any closer, it'll be too hot, the water will boil away. If it's too cold, it freezes. That's a little limited. One of the interesting thrusts of planetary exploration right now is to go look at places like Europa. That's one of the moons of Jupiter, and Sollitt, one of the moons of Saturn, and even Ceres, one of the asteroids in the asteroid belt. What these all have in common is the possibility of a liquid water ocean under the surface. And if there's liquid water, in this case, it'll heat up. In the cases of Enceladus and Europa, it's heated up by tidal flexing of that planet, or of that planetary object, in its orbit around Jupiter and Saturn for both of those guys. If you have liquid water and lots of free energy, you could have life forms similar to perhaps what happens low or deep in the Earth's oceans in deep sea vents. So that could be a completely different kind of habitable zone.
Okay. Another question that we got was we talked about light years in the program, and if we can't travel as fast as the speed of light, do scientists have any ideas of how we might travel to a planet that is light years away?
The short answer is it's really hard. It is particularly hard to send people. I've seen ideas for interstellar probes, which could potentially work, and they involve things like devices called Fresnel lenses. And the idea is you have a large solar sail, and that gets it going. And then as it gets further and further away, the solar sail is use a laser on the solar sail, a gigantic laser that's in the solar orbit. And then you start sending Fresnel lenses. These are thin objects that actually act as lenses. And you send them eventually you have, hundreds of them or something, shaping the beam and keeping it going and keeping the spacecraft going. And it has to be a very, very light spacecraft. Nobody's on board, especially because it would take an incredibly long time to get there. We're talking about a mission that's probably at least 50 to 70 years long, or 50 to 100 years long, just to get to Proxima Centauri, and that's just to fly by. We're not talking about stopping. Just to fly by, get no more than a couple of minutes or a few minutes passing by the planet, probably seconds, but passing through the system, depending on how many planets or how many other things there might be there, minutes, maybe tens of minutes. It's a very small system.
Wow. So there's no easy way to get there yet. No. Okay. Well, we've got Colin Miller is watching, and Colby is also watching, along with Ethan and Sabine from Dallas, Texas. And Brittany would like to know, how deep can we see into space these days?
All the way. Well, we can see with very, very different kinds of telescopes, not just things like an ELT, but we can now look, we've been able to look all the way back to a great wall of radio interference. And this is the primordial leftover noise. It's the cosmic background radiation. And that's actually led to some amazing discoveries about expansion of the universe, about how much matter there is in the universe, how gravity works. Basically confirming Einstein's theory. And that's about 14.6 billion years ago, or 12. Wow. It's as far as it goes back. We can't see past that, because that's really the time when the universe became transparent, and before that it's opaque. However, there is a new way to do it. There's a completely new way to look at the universe through instruments like LIGO. And these are interferometric gravitational wave observatory, plus another one called Virgo, that's in Italy. I think it's in Italy. There are a couple more of them that are coming online, and these look at gravity waves. So these are being used right now to study mergers of things like black holes and black hole pairs, neutron star pairs, black hole and neutron star binaries. And you could, they are trying to use this instrument to look past that wall and see what the very, very early universe looked like.
And apparently that question was from Silas, and Brittany is his mother. So we wanted to clear that up. We have another question. Somebody wants to know, because we talked about cotton candy planets. Can you tell us, how did they form? And, how do we know what they might look like?
We don't. That's the short answer. What we have are models. So what we get out of something like an occultation measurement, we get a few things. We get the period, obviously. We get the diameter. But that also comes from understanding what kind of star you're looking at. Okay. So the orbital period gives you the distance from the star, it's mean, and then the amount of light that's being occulted tells you the diameter of the object. The diameter, you also get, let's see, how do you get the mass of the thing? Well, you get the mass of the thing you get that from radial velocity measurements of a star, for instance. But if you can get the mass of the star, or the mass of the planet rather, and the diameter of the planet, you can calculate what the mean density has to be. And then people will look through their models and say, what does this thing look like? One of the great challenges coming up for exoplanetary research is to start really looking at these things, putting, in fact, the ELTs might be able to help with this, but trying to get light from the actual planet, not from the star. There have been some direct detections, but most of them are things like rogue planets. But if you start getting the light from the actual planet, they were talking about spectroscopy. The students were talking about spectroscopy. You can then look at the constituents of the planet and see what's actually in there. At least in the upper layer.
Is there anything we can learn about exoplanets by studying Earth?
Yes. We can study Earth, we can study our own solar system and the other planets in it to get an idea for what we can begin to populate the rogues gallery of planets. So we actually compare exoplanets to planets in our own solar system. So something with twice the mass of the Earth is called a super Earth. Something with twice the mass of Neptune is called a super Neptune, and 2 masses or 10 masses of Jupiter is called a super Jupiter.
Okay.
We can study our planet, Mars, Venus, to look at what rocky planets look like in different kinds of atmospheric conditions. This tells us a lot about planetary heating, planetary cooling, and so forth. And we can apply those lessons absolutely to what's going on in other worlds. In fact, atmospheric science is crucial, or planetary science is crucial to understanding planets in other solar systems.
Mary Nelson is at Argyle Middle School, and she wants to know how you classify planets.
How do you classify planets? Mostly by mass, and maybe location in the solar system, mostly by mass. Either you have small rocky planets, such as the TRAPPIST-1 system. There are a bunch of, we think, small rocky bodies in that system. Of course, our inner solar system is small rocky planets. And then you have the big giants, things like Jupiter, Saturn, Neptune, Uranus, just like, and a great many planets are thought to be giant gas giants as well. And the difference between them is where they formed, we think. So Jupiter and the other gas giants formed where there were a lot of volatiles that were freezing out, things like water or methane or whatever, freezing out and collecting into these large masses where The rocky planets formed in a much hotter part of the solar system, where the water and all these other things, all these other gases, are hot enough that they're being blasted out. They never coalesce. So that's roughly the idea. So I think that's what. So it's also origin. So rocky and gaseous are really the two.
We actually have a lot of people watching on Ustream. If you have questions, you can email those questions to us at stemin30@si.edu. Elliot, Jacob, and Oswin want to say hello. And somebody wants to know, can you see Proxima Centauri without a telescope?
I don't think so.
Okay.
I've seen photographs of it through a telescope, but not really. You can certainly see Alpha Centauri, and Proxima Centauri is actually part of that system. So it's actually in a very wide orbit around Alpha Centauri A and B. There are two stars there, along with Proxima.
Okay, Emma would like to know, how long typically does it take to build these giant telescopes?
Many years. So this can be a very complicated process. I would guess that building one of these large telescopes is a lot like building a space mission. There's a great many years spent in conceptualization, in figuring out what it ought to look like before anybody ever cuts any metal. But probably in excess of 10 to 15 years.
You were talking earlier about the moons of Saturn and Jupiter. What's the difference between a planet and a moon?
There's the IAU definition. The IAU definition says that a planet dominates the area around its orbit. So in other words, it is the dominant object. There's no other object in its orbit unless it's under the influence of its gravity. So great example, Jupiter obviously dominates its orbit. There are a lot of other objects in the same orbit, moons, also the Trojan asteroids, and those are affected by Jupiter's gravity. They actually gathered at a couple of points in space because of Jupiter's gravity. So Jupiter is considered the planet. The moons are then not considered planets because they orbit Jupiter. They do not dominate the orbit.
Okay. There's a question. How many? Do you know how many Goldilocks zones we found, and about how many exoplanets do we think there might be habitable?
In terms of the number that we have found in the habitable zone, I actually don't have that number off the top of my head, but I think it's at least in the hundreds.
Okay.
In terms of what we think it could be, the low estimate for our galaxy alone that I have heard, it's an old number, so it's probably a bit low, is 500 million. And then the upper limit is more like 20 billion. Okay. So we're looking at billions of these objects of other Earths, in essence, throughout our galaxy. And in terms of are there planets, how many stars have planets? It looks like maybe all of them.
Okay, wow. All right. From Twitter, Jackson would like to know how many nebulas have been discovered?
There I'm stumped. No clue. There are lots of different kinds of nebulas, too. And a nebula is, there's a kind of nebula called a planetary nebula that is one of the natural stages of progression in many stellar lifetimes. So a medium-sized planet can start shedding its outer layers, and that turns into a kind of nebula. But nebulas are extremely common. They're all through every star-forming region in the galaxy, in the universe, is considered a nebula. So they are everywhere.
Jackson, good question. Mrs. Hansen's fourth grade has a couple of questions. How do you name planets when you find exoplanets? What's the naming structure for them?
The current naming structure is that they are named for the system that discovered them. And they're given a designation in the order in which they are discovered and verified. They have to be verified before they're named, I think. there are some exceptions to that. So, for instance, well, eventually they do get named, I suppose. So, Proxima b is a great example. It was actually discovered by a telescope down in South America, but it orbits Proxima Centauri, so it was called Proxima b because it's orbiting the planet. And now there's supposed to be potentially a Proxima b or a Proxima d. So that's one name. But we talked about the TRAPPIST-1 system. TRAPPIST was named for the system. It's an acronym. I forget what it stands for, but that was the system that actually found it. It's called TRAPPIST-1. Not a very prosaic name, but it's I believe that the star that they orbit is not really, so they've kept the TRAPPIST-1 designation. Similarly, for all these Kepler systems, Kepler's, you talked about Kepler 23A or something earlier. Great example of an unnamed star that it was discovered. The planets were discovered by Kepler, so that's still the name. I believe there's a notion the IAU wants to name these things, and they're talking about competitions or something. I'm not sure what.
How do you know when you have found an exoplanet?
A couple ways. So in the film, you guys talked about the occultation method. This is the method where the planet passes in front of the star. And you generally need at least 2 occultations to make sure that, gee whiz, yes, you have a planet in a certain period. You're like 3, you get 2 periods, and 3 generally confirms an exoplanet is there. Obviously, if you get more of them, that's great. So you need to get a number of transits, and you have to be sure that they are, in fact, the same planet transiting to verify the existence of the planet.
I think this is an interesting question. How do the mirrors in these large telescopes work, and why do you need them?
Okay, so what you're doing with mirrors is you are collecting an incredible amount of light. So the reason we have these huge telescopes is they're basically huge light buckets. You want to collect as much light as you can because there's so little light coming off of these really, really dim objects. The other reason you want them big is because you get better resolution. You see finer detail. But you've got 5 mirrors, for instance, in the ELT. What's going on with all these mirrors is that the beam of light that's coming from your target is being collected, redirected, shaped, and brought down to a focal plane. That focal plane this is what's going on in a 35 millimeter camera or even in your cell phone. You have your lens, maybe there might in fact be a couple of them depending on the complexity of the system, and that's bringing it all down onto a CCD. That's the focal plane, the actual chip that reads the current off the light.
Are there any challenges for tests to image exoplanets in our galactic disk?
Not entirely sure I'm following the question. Are there challenges to imaging planets in the galactic disk? Yes. But there are challenges to imaging anything in the galactic disk. It's a pretty cluttered system. If you have a small enough field of view, it might not be that big a deal. We do want to look at we need to look at planets in our galactic disk, obviously, because that's where most of them are.
We've got more questions from Mrs. Hansen's class is very involved today. They want to know when was the first exoplanet discovered?
Long time ago. It was discovered nearly 30 years ago in 1992. And it was, there were a couple of them that were discovered actually at the same time. So there were 2 that were discovered at the same time. And they were discovered in the last place anybody ever thought to look. They were orbiting a neutron star. And this was a shock at the time because a neutron star is what you get after a supernova, when everything is supposed to have been blown way far away from the neutron star. So where did they come from? Honestly, I have no idea. Don't ask me that. But it was actually discovered because the neutron star's signal, its radio signal, it's called a pulsar. It's constantly sending out these radial pulses of light. Those pulses were not exactly the same as in most pulsars. They were just a little bit different, and the only way to understand them was, hey, if we modeled the system by putting a couple planets around it, we get the same signal back. So we think there's planets around that neutron star.
So we talked about in the show that we think that there are billions and billions of these exoplanets, and so my question is, and we've only been discovering these since the 1990s. What were we thinking about what was out there before then?
So before exoplanets were discovered, I can tell you because I was sitting in an astronomy class before 1992, and I know what they told me. And at the time, we thought that planets were very rare. Many astronomers thought they were rare. There was this disagreement. You have to understand that before 1992, we had only one data point, and you can make that look however you like. And there were a couple different competing theories for how planets might have formed. One of them is the idea of a collapsing nebula, as we talked before. A big cloud of gas and dust collapses down, forms a star. One of the possible mechanisms is that some of that stuff forms a disk, and the disk forms planets. That is now the currently accepted model, and that is called an evolutionary model. That is, it evolves naturally out of just initial conditions, in which case planetary systems should be common. There's another model before 92, which was maybe a star passed too close to our own and drew out a big glob or a big disk of material, which then formed planets. That's called a catastrophic model, where you need a rare catastrophe to form a planetary system. And what was taught at the time, what I was taught at the time, is that that was probably the right model, and that therefore there would be very, very few planetary systems out there in the galaxy, and if we could easily be the only one out there. That is obviously not true. Thank goodness. It's much more interesting in the galaxy that way. And the evolutionary model seems to be the correct one.
There's a question here that it's, can an exoplanet go away? And I kind of want to turn that a little bit and say, can these objects disappear from the sky? Like, can exoplanets be sucked into black holes? Is it...
Okay. So in principle, yes, an exoplanet could be sucked into a black hole. If an exoplanet were to join the accretion disk around a black hole, it would probably get disrupted long before it got to the surface. However, if you're talking about, if we have a formed planetary system, can the exoplanet escape? The answer is yes. And it can happen because maybe there's a binary star system, or maybe there's a perturbation because there's a companion far away that comes in, and you can eject these things, and they can form what are called rogue planets. One of the very first, if not the very first, imaged exoplanet was in fact a rogue planet. Just a planet floating through space, no star attached to it. It gets really cold, but these things could still be quite interesting. But they are out there.
Mrs. Hansen's class is really on top of things today. They want to know if exoplanets, like our planets, if they have moons as well.
Possibly. We have 4 rocky bodies in our solar system, and only one of them has a large moon. Mars has 2 moons. They're both captured asteroids. They're very small. But ours is the only one that's very large. And currently, we talked about evolutionary versus catastrophic models. The current notion for how our moon formed is something called the giant impact theory, more colloquially called the Big Smack. The Big Smack model says that a large object about the size of Mars struck the primordial Earth and brought up a large disk of material, which then coalesced to form our own moon. That is a catastrophic model, which means that moons like ours are probably kind of rare. Given that only one planet in our solar system has one like this, that seems that maybe that bears out. But that's only 4 data points, and we'll have to see what happens. Exomoons is what people call them, if they exist around exoplanets. And an open question is, how many of them are there? If there are on the other hand, we have tons and tons of moons around the gas giants. So if there are, when it comes to large planets out that are forming far out, then yeah, there are probably a bunch of moons there.
We want to shout out to Little Big Town Homeschool Group and the folks of Drums, Pennsylvania. Colin Miller wants to know, why are they called exoplanets and not just planets?
They're called exoplanets because they are out there. They are exo. They're outside of our solar system. So when we speak of the planets, we're talking about the planets of our own solar system.
And so these are outside our solar system.
Everything's
Okay, let's see.
actually, I can develop on that for a second. They used to be called extra solar planets is what they were called. Extra solar.
Okay.
Outside the solar system. Exo is much faster and easier to say.
How do you, let's see, we're getting a lot of questions. I'm trying to get to as many as we can. On average, how many exoplanets do we find in a year?
That's been changing a lot, particularly now that Kepler has done its business. We had a major bit of planetary discovery when Kepler was making its discoveries. There are a bunch of systems that right now that are discovering these planets. And TESS, of course, is leading the charge. So the reason I'm being cagey on this is because the rate is highly dependent on the tools that you have available to you, and those are changing year by year right now. And if we launch more satellites like TESS to go look at more of these objects, we'll get a lot more of them as time goes by.
Well, Marty just did a Google search real quick, and when our show was published, was it last week? Yeah, last week, there were 4,126 confirmed exoplanets, and today at 1:30, there are 4,135. So that's almost 10 in a week.
We can get hundreds in a year. But again, it depends on what's looking when. So for most of that, the first exoplanet is 92, right? For the first 20 years, the number discovered is in the tens. And suddenly, with the launch of Kepler, and now with better systems, we're getting hundreds per year, or 1,000 per year, or a couple thousand per year. But that's not going to last because we've now sort of exhausted the possibilities in most of the Kepler data. There might be more data to look at. But we don't have that discovery tool anymore because it's now gone. But we're still looking at that data, looking at the K2 data. So we'll see what happens. I think there's going to be a drop off just because our capabilities are for the moment on the decline until we launch the next thing. But I think we'll begin to see a lot from TESS and the related systems that are following up on TESS observations.
Well, Luke, we are actually over time. We've gotten so many questions, but we want to thank you for joining us today, and we want to thank all of you who joined us and asked these really fantastic questions. I really appreciate you taking the time out today, Luke, to help us out, because I couldn't have answered any of these at all. Next month, be sure to tune in to 7:30. We will be talking about World War II. Thanks, everybody, for watching.